Let's talk now for SN2 reactions. In every chemical reaction, there is a direct relation between the rate at which the reaction occurs and the concentration of the reactant. When we measure this relation, we measure the kinetics of the reaction, right? SN2 reaction, short for substitution nucleophilic bimolecular. Bimolecular means that the two molecules, nucleophile and alkyl halide, take part in the step whose kinetics are measured. A typical one is this one that you see here, a nucleophile, an alkyl halide, and the rate of the reaction depends on the alkyl halide and the nucleophile in the same time, and this is the general rate for the bimolecular reactions. Okay? The essential feature of SN2 mechanism is that it takes place in a single step, without intermediate. When the incoming nucleophile reacts with alkyl halide or tosylate, the substrate, from the direction opposite to the group that displaced or the leaving group. As the nucleophiles come in one side of the substrate bonds to the carbon, the halide or tosylate departs from the other side, thereby inverting the stereochemical configuration. Example, much like an umbrella turning inside out in the wind. The SN2 reaction occurs in a single step that involves both alkyl halides and the nucleophile. But what are the characteristics of SN2 reaction? Understanding the factors in the chemical reaction is a tremendous value. The first SN2 reaction variable is to look at is the substrate, because SN2 transition state involve partial bond formation between the incoming nucleophile and the alkyl halide. It seems reasonable that a hindered bulky substrate should prevent easy approach of the nucleophile, making bond formation difficult. As a result, SN2 reaction occurs only at relatively unhindered seats and are normally useful only with methyl halides and a few simple primary and secondary halides. As you can see here, methyl has the highest reactivity for SN2 reactions and primary halides. Some relatively unhindered secondary can do also SN2, but mostly is methyl and primary halides. Okay? As for vinylic halides or arylic halides, they do not go SN2 reactions due to the fact that nucleophile has to approach to the double bond. So negative, negative, they oppose each other for steric reasons. Okay? This ones does not work, the SN2 mechanism for these ones. Let's move now to the nucleophile. Any species, either neutral or negatively charged, can act as a nucleophile as long as it has an unshared pair of electrons. That is, as long as it is a Lewis base. If the nucleophile is negatively charged, the product is neutral. If the nucleophile is neutral, the product is positively charged. Let's take a look at this well-known example. As you can see here, an acetylide anion, that is a nucleophile, can react with methyl halides and to give an alkylation, as we learned from the alkyne reaction, but in this case goes through, we learn here that goes through SN2 mechanism. Okay? Some general trends for nucleophiles are that nucleophiles go roughly parallel with basicity. Nucleophilicity usually increases as going down to the column on the periodic table. Iodine is more nucleophile than bromine and chlorine. Negatively charged nucleophiles are usually more reactive than neutral ones. As a result, SN2 reactions are often carried out under basic condition rather than neutral or acid condition. What about the leaving group? Because the leaving group is expelled with a negative charge in most SN2 reactions, the best leaving group are those that best stabilize the negative charge on the transition state. This part here is the transition state. As you can see here, a good leaving group has a lower energy on the transition state. That means that the reaction proceeds faster. But who are those groups that best stabilize negative charge? Those are the tosylate first, the most reactive one for SN2. I will explain the structure below. Iodine, bromine, chlorine, OH, and H2OR-, they are all not good leaving groups. It is just as important to know which are poor leaving groups as to know which are good leaving groups. In other words, alkyl fluorides, alcohols, ethers, and amines do not typically go SN2 reaction. To carry out an SN2 reaction with an alcohol, it is necessary to convert the OH into a better leaving group. This in fact is just what happened when a primary secondary alcohol converted into their alkyl chloride by the reaction with thionyl chloride, or an alkyl bromide by the reaction with a phosphorus tribromide. As you can see here, thionyl chloride makes the OH a good leaving group. And after that, after it is made as a good leaving group, it can go through SN2 mechanism, okay? And you see an inversion of the stereochemical configuration because SN2 reaction attack backwards chlorine on this side here. The same for phosphorus tribromide. Alternatively, an alcohol can be made more reactive toward nucleophilic substitution by treating with para-toluene sulfonyl chloride to form a tosylate. Tosylate are even more reactive than halides in nucleophilic substitution. Something to note here is that tosylate formation does not change the configuration of the compound because the carbon-oxygen bond is not broken. This is the para-toluene sulfonyl, okay? This compound here, and this is called the tosylate. That does not break this bond here. This bond is not broken, it's prevented. That's why it does not change the configuration. Let's move now to the solvent. The rate of SN2 reaction are strongly affected by the solvent. Protic solvent, those that contain OH or an NH group, are generally the worst for SN2 mechanism, while polar aprotic solvent, which do not contain OH or an H group, are the best. Protic solvents such as methanol or ethanol slow down SN2 reaction by solvation of the reactant nucleophiles. The solvent molecules makes hydrogen bond to the nucleophile. As you can see here, those that makes possible for the hydrogen bond solvate the nucleophile. So on that way they decrease the ground state energy for the nucleophile. In other words, slowing down the reaction. Okay? Polar aprotic ones increase the ground state energy. In contrast, polar aprotic solvent increase the rate of SN2 reaction by raising the ground state energy of the nucleophile. Acetonitrile, dimethylformamide, dimethyl sulfoxide, DMSO shortly, hexamethylphosphoramide, HMPA are particularly useful for SN2 reaction as a solvent. These solvents can dissolve many salts because of their higher polarity, but they tend to solvate metal cations rather than nucleophiles, anions. As a result, the bare unsolvated anion has a greater nucleophilicity, and SN2 reaction proceeds faster. As a general reactivity for SN2 reaction, the solvent HMPA is the fastest, the best aprotic solvent. Acetonitrile dimethylformamide, dimethyl sulfoxide. Water and ethanol or methanol are not good solvents for SN2 reactions. Let's do some simple comprehension here. Take a look at these two reactions. No need for naming or anything else, just to understand is any of those two reactions SN2 or not. Take a look at the first one, point A. As you can see here, this is a primary halide, good for SN2 reaction. HMPA, perfect solvent for SN2 reaction. The nucleophile here negatively charged, even better for SN2 reaction. So this is for sure an SN2 mechanism. Okay? What about this one here? This has a secondary alkyl halide. This has a polar solvent, a negative nucleophile. But those conditions here makes it not possible to be considered as SN2 mechanism, as an SN2 reaction. Okay, this last one I'm leaving to you. Leave that in the comments below. Is this an SN2 reaction or no? If you have the possibility to explain it, it's even better. Thank you so much for watching and see you in the next video. Peace.